Hello, everyone. So probably most of you know me through my other affiliation from U4Gen, but today I'm here to present you a part of my PhD work. And actually, I will continue on this effective population size subject here, but I will give you a different perspective. So first of all, we need improved conservation strategies. And to do that, we need meaningful indicators in order to assist the adaptation of the populations due to climate change. And thanks to Mariana that presented that before, effective population size is one synthetic indicator that, of course, is puzzling, as we have seen already in this room, the scientists and the constraints. So are there any constraints? So it requires extensive spatial coverage, large sample sizes, sufficient genotyping intensity, and of course, when we have small and isolated stands, then we can probably meet these sampling requirements and we can do model assumptions. But this is very difficult in widespread populations. Okay, so what we were aiming at with this study. So we wanted to explore if we can estimate indirectly effective population size using some basic genetic parameters. And to do that, we followed two different approaches. One was using the mean or the standard deviation of expected heterozygosity, and the second one was to use the standard deviation of the hybridic coefficient. Before moving into the theoretical aspects of these two approaches, I will briefly explain you how we got the empirical data set. So this sampling design is coming from the Gen3 Horizon 2020 project, and here I used 5 different populations, and in these maps you can see the geographical distribution of the species and where our populations are located. And we used the SPED genotyping. I will very briefly explain that here you have one target SNP, which is known to be heterozygote, and then you can capture within 100 base pairs some novel SNPs, 2 or 3. So, some numbers. The 5 species, as you can see, we have SNPs that are after filtering. So we have a range from 7,000 to 17,000 SNPs. And we have the total number of samples here, where we had 20 to 23 individuals per population, and the populations are ranging between 9 to 15. Okay. We also constructed a bioinformatics pipeline in order to get the basic genetic parameters. As you will see, you can also estimate the effective population size using an e-estimator because it's implemented there. But of course, when we tried to do that, it was impossible. We were getting infinite estimations. Okay, so maybe moving back to the past, because all these equations, as you can see, are from the 1970s. So in the first equation, you can see that we have a clear relationship between the effective population size and the theta diversity, of course, given that the mutation rate remains stable over populations. So for the mean heterozygosity, the expected one, you can see also the relationship between the expected heterozygosity and the theta diversity. And then you can also see another equation. It seems more complicated, I know, but keep with me, I will get there. So the variance is also explained, and it also has a relationship with the theta diversity. And using the empirical data set, this is an example of one species. You can see on the first graph up there that when you use the formulas for the mean heterozygosity and the theta, there is a clear correlation. The same goes Also for the second equation for the variance, it was a quadratic equation, so that's why you see numbers here and here. And then you can see also the correlation between these two equations. Okay, so we can say that given that the mutation rate remains stable over populations, and we can indirectly estimate any using just basic genetic parameters. In this case, the expected heterozygosity, the mean, or the standard deviation. Okay, going now to my second approach. And this was based on the standard deviation of the hybrid coefficient. So here we did 2 different simulation sets, and we used the SimBit software. For the simulations, we used some unique and some common parameters. And then, based on the results, we ran some linear models on the, of the standard deviation that we obtained. Okay, the common parameters that we used were the number of loci, the recombination rate, the mutation rate, and the number of generations that you can see on the screen. And then we did 18 independent simulations with 10 populations of the same size. So here you will see that we have 5 different population sizes with the respective numbers and 3 migration rates. So each time we were selecting, for example, a population size of 100 individuals with a migration rate of 0.01, and so on. And after that, we estimated the mean and the standard deviation of the inbreeding coefficient on the 20,000th generation. And we used the original population each time, so the total number of the individuals. And also, we sampled randomly 25 individuals to make 6 subpopulations. And then we ran the linear model. So we have here as the dependent variable the standard deviation of the inbreeding coefficient, and then the explanatory variables, which is the population size, the subpopulation sizes, the migration rate, and their interactions. And this is what we got. So it seems to be statistically significant for the population size, our model. So here you can see the 3 stars. So we thought, does this indirectly infer differences in N as well? And we got pretty excited. So then we said, okay, we need to be down to earth. We need to be as close as possible to a real scenario. So let's do one big simulation where we can use 400 populations. First, we use again the same numbers of the sizes, but in random this time. And we created a migration rate matrix to mimic the spatial distances and to see how the populations interact with each other. And then again, for this simulation, after the simulation was performed, we had 6 subpopulations from each population with 25 individuals again, which is normally what people are going and sampling per populations in the real life. And then we ran again one linear model with the same dependent variable, the population size as an explanatory variable, the marginality, which are the nodes on the border of the migration rate matrix grid, the number of loci, and their interaction. Okay, if we were too excited before, now we were not anymore. So given this real or close to the real scenario, now that we have the interaction between the population sizes in our model, the population size is not significantly anymore. So unfortunately, again, we cannot indirectly estimate effective population size using the standard deviation of the inbreeding coefficient. Okay, so it's not that bad because we found something. We found that both mean and standard deviation of expected heterozygosity actually can be used to indirectly estimate NE. But of course, under the assumption that the mutation rate remains stable over the populations. And also for the extensive data that we have for the standard deviation of the imprinted coefficient, it was a robust exploration that it could not be possible if we just had some empirical data, so maybe we couldn't have proved that. Okay, before I'm getting into my take-home message, I would like to acknowledge some of these people that are in this room now and in the picture, and Bruno Faddi, that I hope that he's online. I don't know if he's online. As I said in the beginning, this part was funded by the Horizon 2020 Gen3 project. And again, I'm going to stress this assumption because I think that it's important to keep that in mind. And when we have genetic data available for a large portion of the distribution of the species, the geographical distribution of the species, then we can indirectly estimate effective population size using mean or standard deviation of expected heterozygosity and potentially assist in some forest management decisions. And thank you very much. And again, here, maybe literally, I would like to take if there are any questions. Thank you.
Thank you very much, Anna Maria. So, are there any questions? Yes, Sandy.
I was wondering if you have tested with the simulations how robust could be these correlations to non-equilibrium populations.
Sorry,
to non-equilibrium populations. I mean, I understand this formula stands while populations are random, matching population equilibrium. So I think with the simulations you are doing, it could be interesting to see if you have non-equilibrium populations, like that they are changing in size, or they have like some post-glacial recognition history. It is still the correlations that I find really stimulating, that you find this significant correlation. Yeah. That is still standing, or how robust is in non-equilibrium situations that I expect that will be quite common in real populations, right? So,
I mean, what we tried. Okay, I have my presentation here, but I cannot go back. But yeah, we had different sizes in the last large population. So it was, I don't know, from 100 to, why I cannot go back?
Can we go back to the slide?
Can I move my slides back, please? Thank you. Okay. Oh, no.
No, after, I think, right?
Yeah. Here. Okay, so we have different population size. So we are sort of mimicking the reality in terms of size, but then for the simulation, we sampled out of them only 25 individuals. And then I guess, I don't know in what extent the migration rate matrix can capture any of these disequilibrized. But I can also check, I mean, the matrix to see and to calculate what is the equilibrium and what is their status. Mm-hmm. But this was the idea, to try to be as close to the nature as possible.
Okay, thank you.
Yep. Any other question? Ooh. How about the Zoom people? I still remind that Christian is offering some present for the Zoom people. But, okay, so If there are no more questions, let's thank again Anna Maria for her very interesting presentation, I think.